Hey guys, in this video I'm going to talk a little bit about work and expand on some of the things that were covered in the textbook, which I think there are some easy things that students trip themselves up on, and I want to try to avoid that if we can. First, what is work? Why do we need work? Really, why isn't force enough to describe the world around us? Well, to answer this, sort of think about pushing an object with a constant force, but pushing it a different distance. So for example, push an object 1 meter compared with 10 meters. Well, it's harder to push an object 10 meters than it is to push an object 1 meter, even if you push it the same force. So force doesn't encode all the information about how hard it is to push objects, and that's what work does. Work says it's harder to push an object 10 meters than to push an object 1 meters. So harder to push is not a very quantitative measure. So really what I'm talking about is that there's a connection between work and energy, which I'm not going to go into in this video, but we will shortly be coming to this topic in class. But for the moment, think of work and energy as being roughly equivalent. How hard it is to do something, how much energy it takes to do something. Okay, so let's start with our very sort of generic picture of work on an object. We have some block, it is moving some displacement delta r, and there's some force acting on it which is not in the same direction as the displacement. The work on this object is F delta r cosine theta, which I hope you're familiar with from the reading. And so the question we should be asking ourselves is, why is this angle even there? Why should we even expect to see an angle in a definition for work? Well, we can think about that pretty simply just by drawing a couple pictures. Consider a constant force in these two situations. If I push downwards on a block with a constant force versus pushing sideways on a block, it's all the same to me. I push the same, with the same force on this block, but because I'm pushing in different directions, in one case, because there's a surface here, this block doesn't move. In the other case, this block moves. So it matters to the block quite a lot what direction I'm pushing on, whereas it doesn't matter much to me. So this angle means that the work that's being done on the block must depend on the angle, basically because of this reason right here. It's possible to push and not move the block, push as hard as you can and not move the block, and therefore there shouldn't be any work being done on the block. So from the reading, you probably already know that this angle right here is the angle between the two vectors. So let's consider another case where it's not so obvious that that is the angle that you're actually being given. And that's this. So the displacement is the same, the force is the same, but the force is acting in a different direction. Now the force is acting back here and at an angle of here with respect to the horizontal instead of here. Well, the expression for work is actually exactly the same, and so that might be sort of confusing because here we have this angle right here, but actually isn't the angle for this force, isn't that the angle right there between F and delta R? Well, it's not, because right here you see that the vectors are tail to tail. We are not adding vectors up here, we are putting them starting at the same point from the origin. So in order to do that, we actually have to move the force so that it's tail to tail with the position, which we can do because actually vectors are movable objects. So I'm going to do that, put that right there. And then it's obvious to see that because this angle and that angle are the same, that's how you get the same expression for the work. F delta r cosine theta. So okay, that's what we expect. We expect the answers to be the same. But so let's consider a more complicated example to try to figure out what angle we actually need to calculate the work. So this is the example I want to do. We have displacement in the same direction, but now our force is pushing instead of pulling at an angle of theta. So how are we going to do the work formula here? This angle is not the right angle. We can't just stick that theta in because it's not between F and R being added tail to tail. So first we need to do is move the force down there. So now F and R are tail to tail, and then we know that this is the angle, I'm going to call it theta prime, that you actually need. And so we can write our work formula as F delta R cosine theta prime. So that's not enough because we have theta prime and we actually want this to be in terms of theta because that's what we're given. But you can actually see that this is a straight line right here. So these two angles are related because they add up to 180 degrees. Theta plus theta prime is 180 degrees. So that means that theta prime is 180 minus theta. And that means that cosine theta prime is cosine 180 minus theta. And if you look up in a trig identity table, you'll see that this is actually negative cosine theta. And so the work is negative f delta r cosine theta. And that's the answer. That's what we want for this. And actually, if you've read the textbook, you know that this negative sign comes because the work being done on this block is negative. We're working to prevent the block from moving. It doesn't mean that the block isn't moving. In fact, the block is still moving. It's still going at displacement delta r. But the work that this force is doing on the block is negative. It's trying to prevent it from moving. Okay, so that's good. But now I want to present another way to look at work, which is, I think, a bit more intuitive, and it gets you to these kinds of expressions, I think, a little bit simpler. And that is that I'm going to call work F parallel times delta r. Now, the textbook doesn't do this. You don't have to use this, but I'd like you to listen and just see what the logic is behind this, because I think it's a bit more intuitive. So the work, this F parallel is the component of the force which is parallel to the displacement. So it's the component of the force that's along the displacement. So if you look up here, what's happening is not the entire force enters into the work formula, but only the part of the force which is along this displacement. That's what this F cosine theta comes from, because F cosine theta is really F parallel. So let's try to be a little bit more specific about this. So let's take that example up there, right? F parallel, and say, okay, I want to see if I get the same answer by calculating what F parallel is. Well, first, because I'm talking about components now, I need to put a coordinate system in, so I'm going to call this X and Y. So the parallel component is the one that's along delta R. X is along delta R, so I'm looking for Fx. And as we know from our triangle geometry, Fx is going to be F cosine theta. But of course, it's in the negative direction because it's pushing in the negative direction, so that's actually negative F cosine theta. And then immediately we get the same answer that work is F parallel delta R. Just plug in F parallel, you get negative F cosine theta times delta R. You get the same answer. Of course you should, but this I think shows a little bit more carefully what, where this cosine comes from. It just makes sure that the force is not the entire force, but it's whatever force is along the same direction as the displacement. So this is a nice way to think about the work, and really the problem is that using work in any given situation, you have to pick which formulation of it you want to use. So I'd just like to quickly summarize the three basic ways that I think about work that will help you think through each problem and figure out which one you want to use. So to summarize, we have the first definition of work, which is a dot product of vectors. And this is kind of the mathematical definition. It's maybe the least likely definition that you're going to use, but this is really where all the other definitions come from. This is the root of all the problems that we're going to have with work, is because it's this complicated kind of dot product thing. The second definition for work is what is in the textbook. F delta r cosine theta, where cosine theta is the angle between F and delta r. This is a nice expression because it's straightforward, it's easy to remember, but the challenge is that you just have to really make sure that this is the angle you're finding. You're not finding some other angle. And the vectors have to be oriented tail to tail. They have to be matched up like that, and this is when you can use that formula. The third formula is the F parallel times delta R, and I think of this as sort of the intuitive formula, or the intuitive definition. And that's just because it not only does it give you a good idea about which force is contributing to the work, but also if you calculate F parallel, you'll get F cosine theta. In fact, if you calculate F parallel, you'll also pick up that negative sign, which is not explicitly part of this formula. So sometimes if you use this thing, you might forget about the negative sign, forget that if the F is going the opposite direction, you need to get a negative sign there. But if you think of this as just a component, then you'll get the negative sign because you're looking for the x component. The x component is going to be negative, or the y component, or whatever component is along the displacement. So I hope this has been helpful in clearing up a few of the confusing things about work. We're going to do some whiteboards on it next class, but thank you guys for watching.